Okay, so where I left off yesterday was the following. So the theorem we were in the middle of proving is this one. So this is showing not only the exact characterization of when this particular Diophantine equation has a solution, but also exactly the form that any solution has to take. So we had shown the first bit, we'd shown that solution in this form is always a solution, and we'd shown that when the GCD of A and B divides the right-hand side, then this thing has a solution. So then the only thing that's left to show is that the solution always is in this form. Okay, so in order to do that, what do I do? Well, so this is what I'm saying here. So all I need to do in order to be done is show that any solution is of the required form. So suppose that say x naught y naught is a solution, i.e. Suppose that a x naught plus b y naught is equal to c, and let say uv be any solution, which of course means the same thing, i.e. AU plus BV is equal to C. Okay. So setting these two equal to one another, since both of them equal C, and say subtracting this second one from the first, what does this mean? This means that A, or I guess whichever, I can do this either way I want to. I can subtract the first from the second. So A times U minus X naught plus B times V minus Y naught is equal to 0. Okay. So then moving, say this to the right-hand side, A times U minus X naught is equal to minus B times V minus Y naught. So changing the order here, this is B times Y naught minus V. Okay. So now looking at this, I'm almost where I want to be. So I'm almost here. To see that, so let D be the GCD of A and B, and divide both sides by B, or by D, sorry. So looking at this expression, divide both sides of that by D. So what I get is A over D times U minus X naught is equal to B over D times Y naught minus V. Okay. All right. So I'm almost there. One thing that I have to be careful about is that in this entire process, I technically haven't. So I have said, as one of the assumptions, that at least one of A and B is not 0. Okay. So in this expression, what were to happen, say, if A was 0, right, and B is non-zero? Then, so in this expression, what we're going to try to say is that this expression tells us that A over D divides the right-hand side. Okay, but if A is the one that is 0, what would that mean for us? So if A is the one that's 0 here, that kind of is a slight problem because A over D itself would be 0, and we wouldn't say that A over D divides the right-hand side, since a 0 thing we don't consider as dividing anything. So what does that mean? Well, if A is actually equal to 0, then if you go back to the original equation, this means that, say, B times y naught is equal to C. Or even, I mean, if A is equal to 0, go back to the original, and I'm not even talking about this, I'm talking about the original Diophantine equation. AX plus BY is equal to C. So if A is equal to 0 in this equation, then this equation is just BY is equal to C. Okay. So in that case, X is free to be whatever you like, and you can easily find the Y in that case. So basically, there's no restriction on X. And in this case, say V is just C divided by B, which is an integer, since this statement is just the one that B divides C. So anyway, and that's exactly the statement of the theorem anyway. In that case, so I would be done. And I mean, similar reasoning if we were going the other direction, saying that B over D divides the left-hand side, then if B were the 0 one, we could likewise say exactly the same thing. Going back to the original equation, we would have AX equals C, and so there'd be no restriction on Y, and we'd be fine. So as long as one of these is non-zero, we're fine, and I don't have to say anything more about this. So for our purposes, just assume that A over D is non-zero, because in that case, you get a more trivial equation, and we'd be done. Okay. So note then that A over D divides this right-hand side. So B over D times y naught minus V. Okay. But what is the GCD of A over D, B over D? So the GCD of AB is D, so then I divide each of them by their GCD, and I think of what is the GCD of this. So we showed this before. This means that this GCD has to be 1. Okay, so GCD of A over D, B over D is 1. And so this previous proposition that told us, so we have A over D divides this product, but the GCD of A over D and B over D is 1, so A over D actually has to divide this other factor in the product, right? So if it's relatively prime to one of the factors in this product that it divides, then this thing doesn't contribute to its divisibility of the product. What does is this other factor, right? That was the intuitive way of remembering that that fact. So what this says is that A over D divides y naught minus V. Okay, i.e., there exists some integer that we'll call t, such that since A over D divides this, it means that y naught minus V is equal to t times A over D. Or, if you like, that V is equal to y naught minus t times A over D. Okay. Well, that's half of what I wanted, right? So that is half of what I wanted. What do I mean by that? Well, going back to my theorem, what is the form for generic solution of y in this, or this component of the solution here, is of this form. Right, that's exactly what I wanted. Okay, so then quickly, what's the last bit? Well, now, what do I... Oop, ran out of room here, so let me continue. Okay. Well, I know that from this statement, a over d times u minus x naught is equal to b over d times y naught minus v. But y naught minus v is some integer t times a over d. So plugging this into this boxed expression here, what do I get? So this means that a over d times u minus x naught is equal to b over d times a over d times t. Okay. So then multiplying both sides of this by d over a, I get that u minus x naught is equal to b over d times t. So u is x naught plus b over d times t. So, paying attention to what I've shown here, I got that u has to be x naught plus b over d times t, and rewriting what I found from before, v must be y naught minus t times a over d. Didn't write it in the same form, but there we go. Now, what did we assume? Well, we assumed that if we started with any particular solution, x naught, y naught, and we let uv be any solution, and we have ended up with our any solution u and v being of this particular form, which is exactly what we wanted to show. So this is it. Okay. All right. So that's how that goes. Now, we have more to say here. Namely, if I assume that a, b, and c are integers, maybe before I state this, it makes sense to say something else here. So I'm gonna stop for a second before I write out this corollary. It makes sense to actually say something in particular. How does this work practically? So practically, practically speaking, what is it that that I have? I start out with an equation ax plus by is equal to c. Now I know that I only have a hope of finding integer solutions to this if the GCD of AB divides C, right? So let's say I call that D. Well, in that case, I can actually simplify my equation by just going ahead and doing that division, right? So I do that division, I get a over d x plus b over d y is equal to c over d, whatever that is. So I actually get another equation, a prime x plus b prime y is equal to c prime, right? Which is going to have smaller numbers. Okay, so this means that I end up with an equation that is simpler in the sense that it's smaller numbers, so it's more likely that I can come up with some kind of just by inspection solution. Okay. And what is nice about this case, so in this, note that the GCD of a prime and b prime is 1, right? We did this was part of our proof, right? So something that fell out of the proof that we just did was that once you've done this, of course, the GCD of a prime and b prime, which are just a over d and b over d, where d's are their GCD, that's 1. So this is particularly nice. A quick example of this happening is 6x plus 15 y is 30. So then their GCD is 3. So we divide by 3, and what we end up getting is 2x plus 5y is equal to 10. So these are the same equation. This is slightly easier to deal with, right? And what it means is that this guaranteed solution that we get is going to be in a slightly nicer form, just because all the numbers involved are going to be smaller. Again, this isn't a huge deal, but this is the idea. So now this corollary that I'm going to write will look a little bit less confusing. So assume that a, b, and c are in the integers, and let's say at least one of AB is non-zero. Okay, then if the GCD of A and B is 1, so for instance, assume that we've already done this simplification that I was talking about, then the equation AX plus BY is equal to C always has infinitely many solutions. Of course, since 1 divides C, it doesn't matter what C is, so this always has infinitely many solutions. And if x naught y naught is a particular solution, then x equals x naught plus bt, and y is equal to y naught plus, y naught minus at for some integer t, i.e. all solutions are of this form. And again, this is slightly simpler expression because here d is 1. So in our previous statement, that GCD that shows up is actually 1. Okay. All right, so that's nice because we are guaranteed, we basically know exactly what it is that's going on. In this case, there's no mystery. You look at the equation, you look at the GCD of A and B, you know immediately whether or not the equation has integer solutions. If it does have integer solutions, all you need to do is find one of them and you get infinitely many, and you know the form that all of them have to take. Similarly, if you've done this process where you've already simplified your equation, if you can't find one of those solutions by inspection, well, then you know that the solutions, again, if you found a single particular solution, then this is the form that any of them have to take. Now, the thing about this is, note I haven't actually given you a method for finding that particular solution. If you had one, either by inspection, because you've made this thing simpler, right? You just look at it and you can immediately pick out numbers that work. Or it was just gifted to you from someone and you checked and it actually worked, then you'd be able to write out infinitely many solutions. But the question is, how do I find x naught y naught in general? So how do I find a single solution to get me going, right? How do I find a solution in this case? So a method of doing this that is always going to work is using the extended Euclidean algorithm. So the answer here is extended Euclidean algorithm always works. Okay. All right. Okay, to see this, let's write, so let's try to solve. So solve 13x plus, say 7y is equal to 5. Okay. Well, here I'm actually in the easier case, so note that the GCD of 13 and 7 is equal to 1. And 1 certainly divides 5. So this thing has a solution. Now all I need to do is to think, what am I trying to accomplish here? Well, since my GCD of these things is 1, and again, regardless of what thing that I started out with, I could always be in this case of GCD 1, and I get to that just by whatever the GCD was that I started out with. I just divide both sides of the equation by that, and then I'm suddenly in this case with GCD is 1. So this process this exact process will always be the thing that you do. So what's the idea? The idea is if I write 13 and 7 as a linear if I write 1 as a linear combination of 13 and 7, I can just multiply by 5, right? So note if 1 is written as a particular linear combination of 13 and 7, so 13x naught plus 7 y naught, then this implies, after I multiply by 5, that 5 is 13 times 5x naught plus 7 times 5y naught. And so actually the solution that I seek is 5 times x naught and 5 times y naught, whatever this x naught and y naught were. Okay. Okay. So so this is what I'm going to do. So using Euclidean algorithm, note 13 is 1 times 7 plus 6, and 7 is 1 times 6 plus 1, and 6 is 6 times 1 plus 0. Okay. So then expressing 1 as a linear combination of 13 and 7, how do I do this? Using my extended Euclidean algorithm, what do I say here? I have 13 and 7 and 6, and then 1 is the last thing that shows up here, and then my columns of x and y here. So thinking of 13 as a linear combination of 13 and 7. Remember, the way that this goes is the entry in the left column is the thing that you're thinking of being a linear combination of 13 and 7. So in this thing, you would have x being 1, y equals 0. Similarly, if this goes away and I rewrite 7 here, then suddenly this is 0 and 1. Looking at the first line here, 6 is 13 minus 1 times 7, so that's first row minus second row. So this is 1 minus 1. That is what I get from this thing, right? So I say 6 is 13 minus 1 times 7. So again, that's first row minus second row. So maybe I'll write that out. First row minus second row is how I compute that. And then to write 1 out here, so 1 is can be written as 7 minus 1 times 6, but 6 is the third row. So that is 7, which is the second row, minus 1 times 6, that's the third row, so this is minus third row. Okay, so what is second row minus third row? So second row minus third row is minus 1 here, and second row minus third row is 1 minus minus 1, so this is 2. Okay. All right, well, this is what we needed. So this implies that 1 is equal to 13 times minus 1 plus 7 times 2, right? This is me writing 1 as a linear combination of 13 and 7. Okay. Well, now I'm done if I think to myself, well, I found a solution to the equation 13x plus 7y equals 1, but that's not what I'm actually looking for. What I'm looking for is a solution to this equation 13x plus 7y is equal to 5. So then I just multiply both sides by 5. So then 5 is equal to 13 times, I'm moving the 5 here, so 13 times minus 5, and here this is plus 7 times 10. Okay. So what this means is that x equals minus 5 and y equals 10 is a solution to my equation 13x plus 7y is equal to 5. Okay. So, by theorem 3.1, so by theorem 3.1, any solution has the form x equals minus 5 plus 7t. Right? Again, we're in the case where the GCD is 1, so rather than just theorem 3.1, also the corollary that followed says that we can write this in an even simpler way, but of course it's the same thing because the GCD is 1, and y is 10 minus 13t. Okay. Okay. Now there's a slight technicality here. So one thing is to note that yes, in this way I found that x equals minus 5 and y equals 10 are solutions. But judging here, right, just setting t equal to 1, for instance, right? So if you set t equal to 1 here, I'm just going to write it up here. So if t is equal to 1, then I get solutions that work equally well. So x is equal to 2, and y is equal to minus 3, right? So x equals 2, y equals minus 3 works, and these are smaller in absolute value than the ones I got here. So let's say that I had started, I just noticed this, right? I didn't use the Euclidean algorithm at all. I just noticed that this worked. Okay, so I noticed I would have 2 times 13 is 26, minus 3 times 7 is minus 21. Oh, sorry, I was pointing at something off screen. So yeah, let's say that I noticed 2 times 13 is 26, minus 3 times 7 is minus 21. So 26 minus 21 is 5. Yeah, that works, right? So let's just say I noticed this. I didn't have to go through this process at all. I just noticed that this was the case. In this case, I could have similarly written something else. I didn't have to write this. I could have written the following. I could have said x is 2 plus 7t, and y is 10 minus 3, or sorry, not 10, minus 3. So y is minus 3 minus 13t. Okay, so here's just following the theorem and its corollary. This is what any form the solution should take. So there might be a little bit of confusion here because it looks like that the set of all solutions I've described by these equations are like different than these. But of course, if you think about it for a second, you know that's not the case. You know that these actually describe the same set of solutions. So it's kind of similar of when you have parametric equations, right? In Calc 3, you can have apparently different looking parametric equations that describe the same line, for instance. So in this case, if you just go through for different t values what x and y values are described here, you get the exact same thing. So the exact same x and y values are described by these two different expressions for x and y. Okay, and so what this means is that if you just glance at any given description of the solutions, it may look different than what you've got on paper, but that doesn't mean that your way of doing it's wrong. Okay, so that's a nice thing to keep into or to take into consideration. So what's something else I wanted to say? So the main thing I wanted to say here is you don't have to use the extended Euclidean algorithm. You definitely don't have to use it. If you just notice, integers that work, you can just say that, right? You can just come up with it by inspection, and then write out the description of the solution. Of course, if I'm giving you this as part of homework or exam, I may ask you specifically to use the extended Euclidean algorithm just to show that you know how to do it that way. But practically speaking, if you just wanted the solutions, you don't have to do it that way. You'd be happy with any old solution that you found, and it doesn't matter what way you found it. You're doing the same thing. The one thing I wanted to say, one more thing, is what if you had an example like this? So let's say minus 17x plus 14y is equal to 30. Okay. So let's say you had something like this. Now in our setup, technically, what's wrong with this? Technically, nothing's wrong with this. This should perfectly be allowed. So then how would I go about using the process that I've described here? Let's say that you couldn't just do this by inspection. How would you go about doing this using the process we've described? So the way that you would do this is you would use, say, the Euclidean algorithm. So this is your idea. So use the Euclidean algorithm to solve 17x plus 14y is equal to 30. Right. So use Euclidean algorithm to solve 17x plus 14y is equal to 30, and then flip the sign of x. And then change the sign of x. That's how you do it. Okay. Okay. So that's a nice way of getting around something like this. Okay. So, that is the end of solving that particular Diophantine equation. So that's a useful tool to have in your toolbox to be able to solve equations like that. So here's a nice related question. So this is the last section in this chapter, chapter 3. So this is called the postage stamp problem. So what is the postage stamp problem? So it gets its name from a framing question, which is to say, what if you went to the post office, you wanted to mail something, right? You wanted to mail a letter, some package, and you only could use, or you found out that they only had stamps of a certain denominations. So in this case, we're going to say 2. We could ask this same question for multiple denominations of stamps, but for us, we're going to focus on just having 2 denominations of stamps. So for instance, say that you go to the post office, you're going to mail something, and you found out that there's only 3 and 5 cent stamps. But the postage value you needed is whatever, it's some integer value, and you had to make it out of those 3 and 5 cent stamps. So then the question that is the postage stamp problem is, can I do it, right? Can I make that integer value that I need out of just 3 and 5 cent stamps? So that's one. Of course, that's just a question of solving, the Diophantine equation I'm solving. In that case, it'd be 3x plus 5y is equal to whatever my postage value was that I needed. But a more general question is, in that case, what's like the entire list of postage values that I can post with those two particular denominations? So using just 3 and 5 cent stamps, for example, how many different postage values could I form just with those stamp denominations? So stating what this problem is in another way, if A and B are positive integers, what positive integers can be written as ax plus by with both x and y non-negative? So we're not restricting ourselves to x and y being positive. And the reason for that comes from just the problem statement. We're totally okay if we use 0 stamps, right? So if you needed 15 cents, then using 3 5-cent stamps and 0 3-cent stamps is perfectly fine. Okay, so x and y are non-negative here. Okay, so this is the question that we're asking with the postage stamp problem. Okay, so this is the statement. What is the idea here? So idea. Let's define any numbers that can be written as ax plus by to be feasible. Okay, that's the definition we're going to use here. So we're going to call numbers that can be written like this feasible. So example, regardless of what a and b are, a, b, and ab are always feasible. Why are those always feasible? Well, again, going back to the postage stamp problem, right? Just thinking about it, if the total postage value I need is A, then I need 1 A stamp and 0 B stamps to be done, right? So that's just saying that, of course, I can always express A as a linear combination of A and B. There it is. I can always express B as a linear combination of A and B. There it is. And of course, AB is just, say, A times B plus 0 times B, right? Or similarly, 0 times A plus A times B in this slot, okay? Okay. So, again, note that this is a significantly less interesting problem if there's not the restriction that x and y both be non-negative. Okay. So this is much nicer. This is a much more interesting problem because there's actually some failure here. You can think for a second why it's less interesting if you allow x and y to be just integers. But anyway, so what is the idea here? So once we define this feasibility condition, I want to draw a chart to see if I can notice the pattern here. So this is how I come to this conclusion. So I'm going to draw a chart. In the top row, I'm going to have numbers. In the bottom row, I'm just going to have a check or not a check telling me whether or not they're feasible. So the postage stamp problem that I'm saying in words, let's say that we have an example where A is 3 and B is 5. So that's 3-cent stamps and 5-cent stamps. Okay, and I want to write the list of positive integers, since that's what we're looking for, which positive integers can be written in this way. So I'm starting with a list of positive integers, and I'm going to check off whether or not they're feasible. Okay, so is 1 feasible? Well, so here, I'll write feasible, question mark. Is 1 feasible? No, there is no way to write 1 as a linear combination of ax plus b, where a is 3 and b is 5, right? And x and y are both non-negative. That's not possible. Similarly, 2 is not feasible, but 3 is feasible. Of course, it's trivial to write 3 as a linear combination of 3 and 5. Okay. Can I write 4 as a linear combination of 3 and 5? You can think about that for a second. I actually can't, right? So the expression I'm looking at here, of course, is 3x plus 5y. I can't write 4 as a linear combination, 3x plus 5y, where x and y are both non-negative. Okay. Can I write 5? Yes, for the same reason I could write 3. It's easy to write 5 as a linear combination in this way. Okay. What about 6? Can I write 6? Well, I could have 3 times 2 plus 5 times 0. That works. So 6 I can write. That's feasible. What about 7? So you can think for a second. Of course, if both x and y are 0, I get 0. If x is 1 and y is 0, I get 3. If x is 0, y is 1, I get 5. If x is 2, y is 0, I get 6. If x is 0, y is 2, I get 10, so that's too big. If x is 1 and y is 1, I get 8. That's as small as I can get here with x and y positive. So 8 is feasible, but what that means is that 7 isn't, right? Is 9 feasible? Yeah, because it's a multiple of 3, so I can have 3 times 3 plus 5 times 0, so that's feasible. 10, that's a multiple of 5, so I could have 3 times 0 plus 5 times 2. That works. And I'm actually done here, but I'm going to go ahead and list some more. So 11, 12, 13, 14, 15. So 11, can I express 11 here? Well, so let's think about it. What would I need to do here? Oh, so I could have 3 times 2 plus 5 times 1, right? So 6 plus 5 is 11. That works. And then for 12, well, 12 is a multiple of 3. So since 12 is a multiple of 3, I could have 3 times 4 plus 5 times 0. That works. How would I do 13? Well, I could have 3 times 1 plus 5 times 2. That's fine. What about 14 here? Can I do 14 here? Well, I could have 3 times 3 plus 5 times 1, so that's 9 plus 5, that's 14. 15 is a multiple of 5, so this is 3 times 0 plus 5 times 3. And we got a lot of feasible numbers in a row. In fact, the rest of them are going to be feasible. So how does this work? So in fact, we get that all are feasible past the point when 3 consecutive are feasible. Why is that? And of course, this is particular to this problem because a is 3 here. So why does 3 consecutive do? So I claim that once I know that I have 3 consecutive feasible numbers, say 8, 9, and 10, the rest of them have to be feasible. So what's the reasoning here? So the idea is that every number past this point differs from one of these by a multiple of 3. Okay. And so in order to get, say, any of these as the linear combination in question, all you have to do is just add enough 3-cent stamps to get the amount that you want, right? So the example it gives is like 92. If you want 92 cents, then what you know is that 92, say, minus 8 is a multiple of 3. 92 minus 8 is 84, which is 3 times 28. And so the idea is that you can just add 28 extra 3-cent stamps, and then you can basically to get the 8 cents you have 3-cent and 5-cent stamps, and then you just add 28 more 3-cent stamps on top of that, for instance, in that case. So that's the idea, and that's why. So it's not always the case that this is 3. It works because 3 here is A. So this is a nice fact. Let's quickly do one more example, and then we'll come up with what it is that we've noticed here. So another example. Let's say A is 2. And B is 7. So the linear combinations we're looking at are 2x plus 7y. Okay, so let's form our table and ask whether or not it's feasible. So is 1 feasible? No. So 1's not feasible. Is 2 feasible? Definitely. 2 can easily be written as linear combination of 2 and 7. Is 3 feasible? No. Is 4 feasible? Yes. You could have 2 times 2 plus 7 times 0. Is 5 feasible? No. Is 6 feasible? Yes. Okay, for the same reason. What about 7 here? Is 7 feasible? Yeah, it's 2 times 0 plus 7 times 1. And I claim that now that I've had 2 consecutive feasible numbers, the rest of them are guaranteed to be feasible for similar reasoning as before. Okay, so 8 is feasible, 9 is feasible, 10 is feasible, and so on. So check, check, check. All these are feasible. Okay. Okay, so what did these tables help me to notice? Let's go back to my previous table. So if I were to look at this little chart and say, okay, what I'm interested in, I guess, is the last number that is feasible, since this sort of thing seems to happen in these problems, that there's a last integer that's feasible, and then past that point, there's a last integer that's not feasible, and then past that point, the rest are all feasible. So how does this work? So note in this case that 7, our largest non-feasible integer, can be written as 3 times 5 minus 3 minus 5. So it's 15 minus 8, right? 15 minus 8 is 7. Okay, remember the integers we use is 3 and 5. So the largest non-feasible integer could be expressed in this way. So maybe, you wouldn't see why this is a big deal, or maybe you wouldn't see this exact pattern until you looked at more of these. So particularly here, let's look at 5. Well, note that 5, our largest non-feasible integer here, can be expressed as 2 times 7 minus 2 minus 7. So 14 minus 9 is indeed 5. So then what is our claim? Of course, we looked at 2 examples here, so maybe we're really drawing too much from this. But from our 2 examples, what is our claim? Our claim is that AB minus A minus B is not feasible. But if n is strictly greater than AB minus A minus B, then n is feasible. Okay. So this is our main claim. Okay. And so we can do this in two parts. So first part is the statement of the first thing. So assume A, B are positive. GCD of A and B is 1. They're integers. I'm not going to write that. So assume that you have A and B positive integers, their GCD is 1. Then there are no non-negative integers x and y with ax plus by is equal to ab minus a minus b. Okay. So we were trying to show that this particular equation here has no solutions. Okay. All right. So, proof. Some standard algebra trickery here. Note that this right-hand side has a particular form. So a times minus 1 plus b times a minus 1 actually is ab minus a minus b. Okay. So x equals minus 1 and y equals a minus 1 is a solution to ax plus by is equal to ab minus a minus b. Okay. Thus, by Theorem 3.1 and its corollary here, since the GCD is 1, any such solution to ax plus by equals ab minus a minus b must be of the form x is equal to minus 1 plus bt, and y is equal to a minus 1 minus at for some integer t. Okay. So this must be the form that any solution takes. Okay. Now, you might say, wait, why are we not... Didn't we just find a solution then? Well, remember, we need non-negative integers x and y that make this true. So we got this solution, but this doesn't work because x is negative. So we want to make x non-negative, right? So in order to get an x value that's non-negative, what do we have to do? We have to choose a value of t that is actually positive. Okay. But this is an issue, right? So to get x greater than or equal to 0, we must choose t greater than 0. But if t is greater than 0, then 1 minus t is less than or equal to 0. Why is that a problem? So let's continue. So proof of that fact continued. Well, note that y is equal to a minus 1 minus at, we said, which can, of course, be written as a times 1 minus t. minus 1. And this, if 1 minus t is less than or equal to 0, then this expression is less than or equal to minus 1. i.e., forcing x to be greater than or equal to 0, non-negative, forces y to be negative. So you can't have both of them non-negative, i.e., there is no solution to the equation ax plus by is equal to ab minus a minus b. Okay, so we have found, oh, I'm off camera. We have found an integer that is automatically guaranteed to be non-feasible, okay, for us. And now we're done with our original intuition here, if we can show that any integer that's bigger than that must actually be feasible. So second proposition that completes our solution to the postage stamp problem is assume a, b are positive integers with GCD 1 if n is an integer that is greater than or equal to ab minus a minus b plus 1, then there exist non-negative integers x and y such that ax plus by is equal to n. Okay. So what's a proof of this? Well, again, if you are looking at our theorem 3.1, what's the idea here? So the idea is that if GCD of A and B is 1, then finding an integer solution to this is no problem at all. So by theorem 3.1, there exists integers, say x naught, y naught, such that a x naught plus b y naught is equal to n, and n, of course, is greater than or equal to ab minus a minus b plus 1. Okay, and so on account of this, I can write any integers as or any integer solutions to this equation ax plus by is equal to n as x naught plus bt and y naught minus at for t some integer. Okay, so this is the form of any solution to ax plus by is equal to n. Okay. All right, so any solution has to be in that form. Now, you are probably asking, why are we not done immediately? Well, the reason why is we have to guarantee that we can have both x and y be non-negative. Right, that's what we need. So basically, the problem, either x or y could be negative. Okay. So then the idea here is to find the solution to our equation ax plus by is equal to n with the smallest possible non-negative y. Okay. All right. And then we'll show that the corresponding x must also be non-negative. That is the idea. Okay. All right. So what is the reasoning here? So the reasoning behind this is that y smaller means x is bigger, right? And so so this is kind of the best way to do it. Using division algorithm if you like, so proof continued by the division algorithm. We divide, say, y naught by a, and write that y naught is at plus y sub 1, where y sub 1 is non-negative, strictly less than a minus 1 for some t. Okay. All right. So this is our choice of y. Okay. So this is our choice of y. All right. So what I mean by that is this is the y that we're saying is our smallest non-negative y. Okay, so thus y sub 1, just using this to rewrite, y sub 1 is y naught minus at. We take x sub 1 to be x naught plus bt as our choice of x. This is the associated x to this choice of y sub 1. So we claim that this x sub 1 choice is non-negative, and we're done in that case. Okay, so by contradiction. So if x sub 1 is not non-negative, then what's like the most it could be? So if x sub 1 is greater than or equal to minus 1, then since by our division algorithm above, y sub 1 is less than or equal to a minus 1, n can be expressed as ax naught plus by naught. But this is a times our x naught here is x sub 1 minus bt plus b times y sub 1 minus or plus at. Okay, so in this way, I'm going to get a times minus bt and b times at. So those are going to cancel, and what I'm actually going to get here is ax sub 1 plus b y sub 1. But if x sub 1 is less than or equal to minus 1, and y sub 1 is less than or equal to a minus 1, so this is less than or equal to a times minus 1 plus b times a minus 1, which is equal to ab minus a minus b. Okay. But this is a contradiction, because I assume that n is exactly, definitely bigger than this, right? So this is contradiction since n is greater than or equal to a b minus b plus 1. So our choice x1, y1 is a non-negative solution to ax plus by is equal to n. And that's it. Okay. So a couple things to note here. One, this is really nice because I mean we've completely determined now which things we can write as combinations of these things. The other, so the other is the following. For instance, you know, there's a really simple application of this if you want. Of course, you don't need this at all, but if you wanted to know, right, like what scores in like a football game are possible, right? Then if you knew that, you know, the smallest increments of scores are 2 and 3, then you're looking for linear combinations 2x plus 3y. But then, of course, the only thing that's not feasible in that case is 1, right? So 1 is the only score that you can't get out of those. But anyway, so let's say that you modified this problem where you had 3 or more stamps. It turns out that it's kind of interesting. It may be somewhat surprising to you that in that case, there's not an analogous formula to what we have here. There's not an analogous thing to determine this so easily. So it's pretty funny. Anyway, so that's a nice application of this early Diophantine equation stuff. I have just enough time to get us into the setup for unique factorization, fundamental theorem of arithmetic. So to do that, of course, going to use this fact. I mean, the most important thing that gets us there is this fact that the GCD of A and B can be written as linear combination of A and B. So we've used that fact a lot already. So then there's the following theorem. So this is chapter 4. So chapter 4. The unique factorization. This is fundamental theorem of arithmetic. So you might say, don't we kind of already have this? Well, you have evidence, of course, pointing in this direction. So the main thing that we already know is that if a number is composite, then it has a prime factor, right? So a number is either prime, or if it is composite, it is divisible by some prime. Okay. So that already gets you a good bit, right? That it doesn't take you too long to figure out how that means, of course, that each integer is prime or a product of primes, because you start out with composite number, it has prime factor, okay, divide it by that prime factor, and you're left with something. That something you're left with is either composite or prime. If it's prime, then you have a product of primes. If it's composite, then it itself has a prime divisor. Divide that, right, by a prime. You're going to get this descending, right, sequence, and at every step you're asking, is it still composite, right? Is what's left over still composite or not? You know what's going to happen. Eventually you're going to end up with something that is prime or is 1, right? So that's where this is headed. So anyway, one big thing that is kind of the only content of 4.1 here. So chapter 4 really only has like a couple of sections here. 4.1 is really basically a single theorem, which is the following. So this is let P be prime and let A and B be integers with P dividing AB. Then P divides A or P divides B. So you have a prime dividing a product of two integers, and this tells you that the prime divides one of them. You can contrast this, and I'll say more in a second, you can contrast this with the case of a composite in this situation. If you have a composite number dividing the product of two integers, in general, you can never say that it divides one or the other. Okay. There's a really, really easy example of this. So 6, right? 6 divides 6, right? But 6 is 2 times 3. So 6 divides 2 times 3, but 6 doesn't divide 2, and it doesn't divide 3. All right, so that's like a really dumb way of coming up with this example. You can always do that for a composite number. You have a composite number AB, then AB divides AB, but AB does not divide A or B. Okay, so that's a really easy way of doing it, but so this is just totally not true for composite numbers, but for primes it is. So to see how this works, I very much make use of this fact of the GCD being expressible as linear combination. So what do? So let D be the GCD of A and B. Okay. Sorry, not A and B. What am I doing? So let D be the GCD of A and P here. Okay. Then, by virtue of the fact that D is a common divisor of A and P, D divides P. But P is prime, so this means that D is 1 or D is P. Right. If D is equal to P, then D divides A implies P divides A, since D is equal to P. So we're done, because we just needed to show that it either divides A or B. So we have taken care of the case when D is equal to P. So let's consider the case when D is equal to 1. So if D is equal to 1, then we can write 1 as a linear combination of A and P. So 1 is equal to AX plus PY, where X and Y are just some integers. Once you have this, and this is, again, as I mentioned before, this is something that you're going to do a ton in number theory proofs. So here I multiply both sides of this by B, so I get B is equal to AB X plus PB Y. Okay. Well, note that since P divides P, trivially, it divides this term in the linear combination, and P divides AB, right? This is the assumption. We are assuming P divides AB. So P divides AB, so it divides this term. P divides P, so it divides this term. This implies P divides B, since B is a linear combination of those. And so I'm done. So just recapping here, if I let D be the GCD of A and P, by the fact that it's a common divisor of A and P, it divides P. If it divides P, which is prime, D is either 1 or P. But in either case, if D was equal to P, it divided A, and if D is equal to 1, then then P divided B. I shouldn't say it here. The only reason this works is because D was equal to P. So if D was equal to P, then P divided A. And if D is equal to 1, then P divided B. And that's why I'm done here. Okay, so as I said here. Nice remark. So warning, I should call it. If n is composite and n divides AB, we cannot say that n divides A or that n divides B. You just don't get that, right? So note, what if n is equal to AB? Right? So that always works. So then n divides AB, but n does not divide A and n does not divide B, right? If we let it be non-trivial, right? So let A and B both be between 1 and n here. Okay. Right. Okay. So this is an easy way to come up with it, but I mean, you don't have to, right? So here's another example. So 6 divides 8 times 9, but 6 does not divide 8, and 6 does not divide 9. Right. Again, tons of examples here, so got to be careful. One more thing, and then I'll be done for today. So corollary of this theorem that we just proved, let P be prime and let A1, A2, A3, all the way up to AR, that's what the textbook uses in the statement, be integers such that P divides the product. Okay. Then P divides AI for some I. So if you have a prime dividing a product of a list of integers, then it divides one in the list. Okay. Again, for composite numbers, this just isn't true. Okay, but it's true for primes. So proof, you might have guessed, is by induction. Clearly, if P divides A1, then P divides A1. So base case R equals 1 is true. Induct, do the inductive step. So what's the inductive step? So suppose that the statement is true for R. Want to show it is true for R plus 1, right? So let A be, say, A sub 1, A sub 2, all the way up to A sub R, and let B be A sub R plus 1. Right. So assume P divides AB, right, which is this list. A sub 1, A sub 2, all the way up to A sub R times A sub R plus 1. Okay. By our theorem, P divides one of them, right? P divides A or P divides B. But if P divides A, since A is this list by the inductive hypothesis, P divides A sub I for say, I between 1 and R. Right. If P divides B, then P divides B is just equal to A sub R plus 1. So this implies P divides A sub I for some I, satisfying I between 1 and R plus 1, which is exactly what we're trying to show. So we're done by induction. Okay. And so that is the proof. So next class on Monday, we're going to be finishing up chapter 4 entirely with fundamental theorem of arithmetic. I thought I might get to it today, but I didn't. I spent a little bit more time on the postage stamp problem, which is fine. So that's the deal. So remember, you have office hours here in a couple of hours. I think I said from 2 to like 3:30-ish. I'll be holding office hours, so I'll just be hanging out here in a stream. You can stop by and ask questions. I'll just be sitting here waiting for questions to be asked. And you have homework that is due tonight. Like I said, if you have to turn it in over the weekend or something, that's not the biggest deal. But soon I'll be assigning a couple more homework problems for you that will be due maybe like Tuesday. It'll just be a few problems from the last couple sections, from chapters 3 and chapter 4, like I said. So I'll have that due like Tuesday, and I'll assign that a little bit later, or maybe tomorrow. So anyway, that's the plan. So I will see you if you stop by office hours. I'll be there. Otherwise, keep a lookout for homework announcement that I'll make later. So I will see you all on Monday. Otherwise.